So, welcome to the lecture 8. So, this lecture will be discussing about the use of the temperature, the weather parameter as a growing degree days concept for the growth duration of phenological development predictions and the yield predictions. So, earlier classes we have discussed about the solar radiations, the effect of solar radiations, how on the crop growth and development, how solar radiations used for the biomass and the yield simulations, particularly the biomass accumulations, the radiation interceptions and the crop parameters, extinction coefficients, radiation use efficiency and the variable you are using the leaf area index, how these are used for the radiation interceptions, biomass accumulations and the grain yield predictions. So, with solar radiations, now today this lecture will discussing the temperature, how temperature plays a role like predicting the developmental phases. The solar radiations is influencing the growth rate, biomass accumulations and the temperature influencing the growth durations or the developmental phases predictions. So, with this that is as a driver of the crop growth, particularly that govern the crop growth, development and productivity, as you discussed earlier. Growth and development they are the parallel. Once there is a good growth, then development happens, transformation from one phenological phases to another phenological phases. So, this temperature plays a role, particularly the development, transformation from one phase to another phase. So, each crop has a specific temperature range. So, each crop has the cardinal temperature as a minimum temperature, optimum temperature and maximum temperature. So, when the temperature remains optimum for that it is crop specific, every crop has the separate temperatures, minimum temperature, optimum and maximum temperature. So, when the temperature optimum, the crop growth attains to at the maximum levels. For any temperature beyond optimum, that is a less than optimum temperature or the higher than optimum temperatures, the growth rate that is affected. And accordingly model there is a text case for temperature factors. For the optimum temperatures it gives the peak growth rate and for the temperature beyond optimum the growth rate is slowed down. So, crops are now classified as per their the temperature requirement. There are the cool season crops and the warm season crops, that is a wheat, barley, oat, potato. These are the crops grown during the winter season or they require the low temperature. The crops like the tropical crops, subtropical crops you can say rice, maize, sorghum, sugarcane and many millets are also they are grown during the particularly the monsoon seasons June, July to December. So, the cardinal temperatures say minimum, optimum and maximum temperature for different crops you can see just a for the cool season crops, particularly the wheat, barley, oat, potato, many vegetables. So, the minimum temperature around 5 degrees Celsius, optimum temperature is 25 to 30 and the maximum 30 to 35. So, similarly for the warm season crops, so minimum temperature 10 to 20, the optimum 30 to 35 and the maximum more than 35. So, these are the range of temperature, optimum temperature where growth rate remains maximum and the crop attains a good growth provided the other conditions also optimum, because soil is not short of the moisture, soil is not short of the nutrients and the crop is well protected from pests and diseases, then the crop attains the maximum growth or the peak growth with the optimum temperature. And of course, other parameters like lights and humidity and wind velocity, those parameters has to be maintained at the optimum levels. So, the growth rate increases from minimum to optimum, then declines the beyond the maximum temperature. So, any temperature the below the minimum temperature or the beyond the maximum temperature the growth ceases, because the crop has the basic minimum temperature and the crop has a maximum temperature. If the temperature goes below the minimum or the beyond the maximum temperature, then the crop growth is ceases. And the physiological response to temperature, because at the optimum temperature particularly the crop growth happens because of some growth hormones. There is a growth regulators, the hormones that promotes the growth. There are some hormones formation that inhibit the growth. like the growth promoters are the auxins, gibberellin, cytokinins, and the growth retarder or the inhibitors are the abscisic acids. So, at optimum temperature or in the range of the optimum, because optimum temperature range. So, in the range of optimum temperature, there is a higher production of the growth promoter, auxin, gibberellin or the cytokinin, and the lower production of the growth inhibitor, the abscisic acids. So, the crop growth attains at the maximum rate, but when there is the minimum temperature or the temperature is beyond optimum, there is a imbalance between the growth promoter and the growth retarders, where the growth inhibitors production is higher as compared to growth promoter. So, the crop growth is affected with the temperature beyond the optimum temperature. At extreme high or low temperature, there is a hormonal imbalance that happens. So, that causes the reduction in the crop growth. Similarly, the temperature that also regulate the photosynthesis, there are many enzymes that are mediated activity, the photosynthesis process, the enzymes are activated, the activity of enzymes are higher at the optimum temperature. So, temperature the beyond optimum, the enzyme activity also slowed down. Similarly, the carbon dioxide uptakes and that also that influenced by the temperature. At optimum temperature, the uptake is the optimum, and the temperature beyond optimum, the uptake is the CO2 uptake, the leaf is also reduced. High temperature stress also that causes stomatal resistance, that also reduces photosynthesis. So, same also with temperature that influenced by the photosynthesis and ultimately the conversion of photosynthetates to the tissue formations, or you can say dry matter productions, that also that depends upon the temperature. With the optimum temperature, there is a higher formation of dry matter. With the high, the excess heat or the maximum, the temperature is beyond optimum, beyond the maximum temperature, that causes heat stress. Heat stress that during the particularly the most of the field crops, or the even if the orchard crops also, if there is a high temperature during the flowering, the very critical stages and the grain filling periods. So, that causes the huge reduction in the grain yield, because during this the critical phases, either the flowering or the grain filling, optimum temperature that causes the maximum production. So, temperature beyond optimum temperature, that causes the grain sterility also. In case of the cereal crops, grain sterility happens because of the excessive temperature, heat stress, that causes the sterile grains. So, that is optimum temperature is very essential. Maintenance of temperature is essential for the maximizing the crop growth. So, it is a very difficult for this in case of the open field conditions. So, most of the crops you can say large scale, commercial scale, we grow under open field. So, very hard to control the temperature. So, only in case of the controlled environmental experiment or greenhouse conditions where the temperature can be maintained, but it is very expensive, where only the cash crops we can grow there, but normal field crops like where you need the large quantity, they are grown in the open field conditions, but there is because we have to see other management condition, how we can modify the microclimate, so that the crop does not suffer from the temperature stress, or we can change the cropping crop planning. So, like adjustment of the planting window or sowing window or the field level management, so that you can nullify the adverse effect of the temperature stress. So, how the temperature used particularly for the simulations. So, every crop they require a thermal units for transformation from one developmental phases to another developmental phase. So, that you say as the growing degree day. So, that is calculate that is that we say as the thermal unit, that is a summation of the Td minus Tb. So, Td is the daily average temperature, Tb is the base temperature for the crop. So, daily average temperature you can calculate from the daily maximum temperature or minimum temperature by 2 as you calculate the daily average temperature, that is a day specific, but the Tb base temperature is a crop specific. So, they have the different base temperature. So, this base temperature varies from the crop to crop. So, there is the growing degree, the thermal unit accumulations of over the durations. Every crop they require a certain amount of the growing degree days. It is expressed as the degree Celsius days. For transformation from one stage to another stage. So, once the crop accumulate that quantity of the growing degree days, so that is the phase transformation that maybe you can give a crop example rice, that from the suppose tillering to panicling sessions that needs certain amount of the growing degree days. Similarly, from flowering to maturity that needs a certain amount of the growing degree days or thermal units. So, once the crop accumulate those thermal unit, then there is a transformation from that developmental phases to another developmental phases, that is a development, and that is most regulated by this temperature. And to some extent maybe radiations that happens, developmental phases may get delay. The crop is exposed to maximum daylights. This happens where the daylight is increase almost 20 hours or the 22 hours, then there is a delay in the developmental phases, maybe flowering or the grain formation is delayed because of the some type of the higher exposure, the longer exposure to the day length. So, the base temperature we can say that the crops have different base temperature. So, rice has the base temperature 9 degree Celsius, wheat 5 degree Celsius, maize 10 degree Celsius, palm millet and 10 degree Celsius. So, when temperature is below this base temperature, the crop growth ceases. There is no addition of the growth if the day temperature remains below 9 degree Celsius in case of rice, in case of wheat below 5 degree Celsius, maize 10 degree Celsius. So, these are the applications. So, this particularly we apply this growing degree day concept for the predicting the crop phenology or the different duration of the crop phases. Also that helps the estimating the yield potentials, seedling irrigations and the nutrient application based upon the developmental phases, because we predict the developmental phases accordingly. We recommend for the nutrient management or the irrigation management for the different growth phases. Then also we forecast the harvest dates based upon the growing degree. So, we will give you an example how to explain the use of the growing degree days in the calculation of the or the predicting the developmental phases and the yield formation. So, in case as you are discussing the take example of one crop, suppose we are going for the rice crop. This is the time x axis and y axis is your biomass. Gram per meter square. As we have explained in the earlier class, the growth curve like the sigmoid growth curve, and as initial slow growth that increases and then remains the plateau, then decreases. And if you see you have explained this stage and this stage, this is the stage of flowering and this is the stage of maturity. So, now we will explain how the temperature or the growing degree concept is used to predict this is the grain filling duration. This is the grain filling duration. So, how the growing degree concept can be used to predict the duration required from flowering stage to maturity stage, the grain filling duration. So, the crop requires certain amount of growing degree days. For example, rice crop requires from flower the GDD growing degree day from flowering to maturity. From flowering to maturity. So, I have written the FL is the flowering, MT the maturity. Suppose the crop requires around 400 degrees Celsius days from flowering to maturity. In case during that period, during the growing period flowering to maturity, the daily T max, in case of daily T maximum temperature suppose 30 degrees Celsius, and the daily T mean, suppose 20 degree Celsius. So, during this period the crop receives the average daily maximum temperature 30 degree and the average daily minimum temperature 20 degree Celsius, and suppose the best temperature for the crop as we discussed just, that is 9 degree Celsius, and from here if the crop requires 400 degree Celsius days for completion of the stages from flowering to maturity, and during that period the T max, average T max is 30 degree Celsius, average T mean 20 degree Celsius, and the best temperature is given 9 degree Celsius. So, now you have to calculate what is the number of days required by the crop to complete the phase from flowering to maturity, that is a grain filling durations. So, we can that is a, if you see the daily average temperature, that becomes 30 plus 20 by 2, 25 degree Celsius daily average temperature. Now, you see the daily accumulation of the growing degree day, if you see the GDD for each day, that will be TD minus TB, that is equal to 25 minus 9 is equal to 16 degree Celsius for each day. So, that is the accumulation of the growing degree day thermal unit 16 degree Celsius. So, the crop needs 400 degree Celsius days accumulations. So, number of days will require. So, number of days for completion of this stage, how much? Because you need the 400 the GDD, the 400 degree Celsius days, the 400 divided by 16, each day accumulation 16, that becomes 25 days. That means the crop takes 25 days for transformation from flowering to maturity, or the grain filling duration that takes around 25 days. So, how this is influenced by temperature? Suppose you have the daily max temperature 30 degree Celsius, minimum 20 degree Celsius, then it takes 25 days. What happens if temperature increases? Suppose in case the T max, suppose that becomes 35 degree Celsius and T mean is equal to 25 degree Celsius. In this case, what number of days required? In this case, you see that daily average temperature, that becomes 35 60, that becomes almost 30 degree Celsius daily average temperature, and the base temperature 9 degree Celsius. So, 30 minus 9 21. So, the days required will be 400 by 21 is equal to so around 19 days. So, that means when there is a temperature 30 degree Celsius and 20 degree Celsius, the average temperature is 25, the crop needs 25 days for completion of flowering to maturity. When the temperature increases, the duration becomes shorter, the crop takes 19 days for completion that phase. In this case, what will happen? If there is a high temperature, the growth rate becomes very fast, and there is a grain filling also, grain filling reduces, the number of days reduces. In that case, there will be loss in production. Every variety they require a particular thermal unit for the completion of that phases in the optimum condition, near to optimum condition. If that condition, if the temperature becomes excessively high or beyond the optimum, either the below or the more than beyond the optimum, in that case what happens? If there is a high temperature, the duration becomes shorter, then the yield is decreased. If there is a low temperature also, that in that case also duration becomes longer, yield also reduced, because the growth rate will be very low. So, you need optimum growth rate and optimum duration to maximize the productions. In such cases, if the temperature remains beyond optimum temperature, growth rate becomes lower or lower in both the cases, and some cases in case of high temperature the duration becomes shorter, in case of low temperature duration becomes longer. So, that affect the output, total output, the grain yield of the crops. So, this is how the use of the temperature concept as a growing degree concept for prediction of different growth phases. Now, how this can be used, because when you are discussing the just last class using solar radiation interception, you can predict the biomass because of the but any point of time, suppose flowering you want to know the biomass. So, at this moment you can know what is the biomass gram per meter square. Before flowering, suppose there may be panicle initiation stage, this one panicle initiation stage, the PI stage. Here also we can predict what is the biomass based upon the radiation interceptions and then biomass accumulation. So, here we can go for the prediction very stage specific. We can, if you know the prediction from PI, we can also predict what could be the biomass at flowering. If you know the LI during this periods, what model does? Model the daily time step. When you go for the crop model, the model calculate the biomass each and every day gram per meter square based upon the radiation interceptions and the leaf area index. Leaf area index also the state variables, and using the parameters like K and the radiation use efficiency, the model simulate the biomass on each and every day. But if you want to calculate the biomass, suppose PI and panicle initiation or flowering stage, if you know the average leaf area index during that periods, we can know the what is the growing degree days from PI to flowering, we can calculate the number of days required for completion of that phases from PI to flowering, and based upon that, if you know the number of days and if you know the, because the some radiation interception, you can calculate the growth rate. Growth rate gram per meter square per day, and from the that comes from the solar radiation. Using the radiation interception, we can calculate growth rate, and you have the already have discussed earlier the radiation interception, you have the leaf area index already variable is given, then parameters are there, the K extinction coefficient and the radiation use efficiency. We can calculate the growth rate gram per meter square per day. Using this temperature, we can calculate the growing degree days, the growth duration. Growth duration, that is the day, that can be calculated using the growing degree day that comes from the temperature. So, using temperature interception, we can calculate the growing degree days. So, you multiply the gram per meter square day into day, so that you can calculate the growth, the biomass at any point of time. If you know the days, this one, and the earlier panicle initiation biomass is known, and the biomass accumulations during panicle initiation flowering, if you know the growing degree days, that gives number of days, and the growth rate gram per meter square day, multiply that one, you can calculate how much biomass can be accumulated from PI to flowering. And if you know the biomass before PI and PI to flowering biomass can be calculated from here, we can calculate what the biomass at the flowering stage. So, the beauty of this one, using this now weather parameters, radiation and temperature. Radiation is used to predict the growth rate. Each and every day we can do the predict gram per meter square per day, and temperature or the growing degree concept is used to predict the growth durations. If you know the growth rate, you know the growth duration, multiply growth duration, that will give the biomass at the end of the particular phases. So, this is how this radiations and the temperature concepts, they are used for the biomass simulations, and already yield we have discussed earlier how yield can be simulated. In the normal scale, if you see a particular crop, you can calculate up to maturity how much radiation interception, the sum of Ri based upon the this leaf area index and the K parameters, K value and the radiation use efficiency. We can calculate the summation of Ri, and you know the RUE. So, multiply this RU discussed earlier radiation use efficiency into Ri, that will give biomass, and multiply the harvest index, already I have discussed last class, that will give to the final yield. that can be calculated. So, these are the steps how you can use the radiation and temperature, these two other parameters for the biomass and yield simulation. So, this will be this concept particularly used for the crop modeling, the radiation interceptions and the temperature accumulation, thermal accumulations for the growth rate predictions and the developmental phases predictions. Then see this is the temperature stress and crop response already we have discussed earlier. So, there is a high temperature stress, there may be low temperature stress. So, in case of the high temperature stress, so there is a pollen viability, that the flowering period. So, that is and fertilization that causes less grain filling. The sterility happens because of very high temperature during the flowering periods. And this also affect the shoot growth and the root growth of the crops, then mineral nutrition uptake and enzyme activity of discussed because of the temperature stress that affect the whole crop growth is affected because of the temperature stress conditions. Similarly, low temperature that affect the cell divisions and the cell elongations, photosynthetic rates and the water transport also reduced with the very low temperature, and the grain filling also ripening also reduced. So, the other thing I want to say, if the as you are discussing this this is the growing degree day, when the temperature concept comes in all cases, that if the TD, the cases TD that if TD is less than TB or TD is greater than the T max of the crop, then in both the cases the GDD that becomes 0. So, both in the daily average temperature less than the base temperature or the higher than maximum temperature. So, there will be no accumulations of the biomass, the crop growth ceases for the both the temperature. So, this is what there is no development, the crop remains under the stagnant phase. So, with this the summary and the takeaway for this, the temperature is the major environmental determinants for the crop growth and yield. So, each crop has a specified defined range of cardinal temperature, it is a minimum temperature, this is a base temperature, optimum temperature and maximum temperatures. So, temperature beyond all this minimum and the maximum, that crop growth is likely to be ceases. No, there is no development and the growth of the crop. And the growing degree days provide the quantitative framework to link the temperature and crop development, and also GD helps predict the phenological events and finally the yield formations. So, maintenance of optimum temperature is highly essential for the maximizing the crop output, maximizing the productions. So, this GDD concept is and the radiation interception as earlier class, they are both used for the crop yield predictions, and that also decides that also advises, give advisory for the proper input management to maximize productions and make a sustainability in agricultural growth. With this, I thank you all.